Hi, in this video I'm going to go over Worksheet 3.3 and talk about the solutions for that. So the first one says, at what points on the graph above, meaning this graph over here, is the object moving most slowly? This is a position here. This is a position versus time graph, right? So the slope of a position versus time graph is going to give us the velocity. So we're looking at the slope. So the places where it's going the most slowly is the flattest. So that would be B and F. So B and F, because that is where the slope is the flattest. There, the flattest. All right, next up, over what intervals of the graph above is the object speeding up? So speeding up would be going from flat to steep, right? So we're looking for places where it's going from flat to steep. So that would be the BC and the FG. So those are the places where it's speeding up. Over what intervals is it slowing down? So slowing down would be going from steep to flat, right? The opposite is steep is fast, flat is slow. So it'd be going from steep to flat. So places where it's going from steep to flat would be A to B and E to F. Okay, cool. Next up, at what points on the graph above is the object changing direction? So, right, if it's changing direction, we're going from a positive slope to a negative slope. Or vice versa, right? So that would be at B and F, right? Because at B, it's going from a positive slope to a negative slope, and from at point F, it's going from a negative slope to a positive slope, right? So there you go. Moving along, right? We have an object that's traveling upwards at a velocity of 30 meters per second. Draw a quantitative, meaning with numbers, position versus time, velocity versus time, and we're going to use -10 instead of -9.8. So the Paul equation tells us where that object is at a given time. So I want to know where it is, so I'm looking for x. Technically, it probably should be a y because we're looking at vertical distance, but since the graph says x, I'm going to use x. It starts from the ground, so it starts at 0. Initial velocity is 30 times 1 second. It's 1/2 -10 1 squared, and that's going to give me let's see here, that's going to be 30. 1/2 times my -10 is right -5, so that's going to give me 25. So then I come over here and I plot at 1 second 25. So it gives me 1 point there to put on that. And then I'm going to do the same thing, but with 2 seconds. See here, that's going to be 60 for 2 squared is 4. 4 times -10 is -40 times 1/2. So it's going to give me 60 minus 4. Oops, what did I just say? 20, which is going to give me 40 meters. So plot here 40 meters. I'm just going to go ahead and do the rest of them on my calculator. So I have 30 times by 3 plus 0.5 times by -10 times by 3 squared. And that gives me 45. Then I'm going to do it with 4, so that's 30 times by 4 plus 1/2 times by negative 10 times by 4 squared. That's going to give me 40 again. And then I'm going to do it with 5, so 30 times by 5 plus 1/2 times by negative 10 times by 5 squared. It's going to give me 25, 0. So I just keep using the same equation. I just keep changing out the times for the next one, right? Change it out for 3, change it out for 4, change it out for 5. And what you should get is this parabola, upside down parabola, looks like that. For the velocity, right, we know that its initial velocity is 30, so we know it starts there. Then a couple ways you can do it. You could just use the Paul equation. So and do the same thing. So basically find out its final velocity. You know its initial velocity is 30 plus negative 10. 1 second, you're going to get, of course, 20 meters per second. But you can also just think about what this means, right? Negative 10 meters per second squared means that your velocity changes by, right, decreases by 10 every second. So if I'm going 20 meters per second, the next second I'm going to be going 10, the next second I'm going to be going 0, the next second negative 10. And I can keep plugging in, numbers here, right? I could plug in 2, plug in 3, and I'd get the same thing. So there you go. And the acceleration graph, right? Your acceleration graph just is negative 10, right? Because it's due to gravity, it's just going to be negative 10 the entire time. So it doesn't change. So there you go. That's that one. All right. Going along. A stunt car driver testing the use of airbags is driving at a speed of 25 meters per second for 100 meters. He applies the brakes and accelerates uniformly. Accelerates means to slow down in this case, to a stop as he reaches a wall 15 meters away. Okay, so in total, they go 150 meters. So this is a qualitative position versus time graph, which means that you don't need to have numbers. I'm going to go ahead and put numbers on it just because I think that's going to be helpful for me. So I'm going to put, it's got to go all the way up to 150, right? So if I go by 25s, that should work pretty well. There we go. Perfect. I'm up to 150. So I don't know anything about the time axis, so I'm going to just leave the time axis blank, and I'm not going to put anything there. So after a certain amount, right, when I get to 150 meters, I'm going to start at 0, I'm going to go to 150, and I'm going to do that at a constant speed, right? Constant speed means constant slope, right? So that is going to be a constant slope is going to be a linear line. So do that. And then it comes to a stop. Stop, right? Stop means flat. So that means by the time I get to 150, it's better be flat. So it's just going to kind of curve and slow down and be flat by the time it gets to 150. So that's going to look like that. So same thing for the velocity versus time graph. We're going 25 meters a second. So it's 5, 10, 15, 20, 25. So for the first amount of time, you're just going 25 meters per second. And then at some point later, you're going 0. So that velocity needs to decrease to 0. How long does it take the car to go the first 100 meters? Well, you're going at a constant speed, so x is equal to vt. You go 100 meters at a velocity of 25 meters per second. What time is that? Right, obviously, that's going to take 4 seconds. T is equal to 4 seconds, right? 25 meters the first second, 25 the second, so 50, 75, 100. So then part C is remember that the area underneath the velocity versus time graph equals the displacement of the car. So here's our velocity versus time graph on the right over here. How many seconds must the brakes be applied for the car to come to rest in 50 meters? Okay, so here's what this is saying. It is saying that the area underneath the graph, so this area right here, which is a triangle. So let me shade that in for you. Okay, it's telling you that area right there is equal to 50. So 50 meters. Okay, so it's a triangle. So area of a triangle is 1/2, right? Area is equal to 1/2 base times height. Okay, so my area is my displacement, and my displacement is 50, right? Um, the the base is the time, right? So this right here is the time that it takes to slow down, and my height is 25. So solve for t. T is equal to 4 seconds. So just like to note real quick, you could do the same thing on this side, where because this area would be equal to 100, right? That rectangle, that would be a rectangle, so that you could do it that way too. Okay, so now it says a quantitative number, which just means with numbers. So that means 5, 10, 15, 20, 25, 1, 2, 3, 4, 5, 6, 7, 8. So horizontal for 4 seconds, and then 4 more seconds to come to rest. So there it looks like that. And then the accelerate, right? Find the acceleration. So there's a couple ways to find the acceleration. You could either find the slope of this graph. So you could either find the slope. So the slope would be right, it goes down 25. So right, rise over run. Negative 25 meters per second over 4 seconds, which would give you, right, 25 divided by 4, 6-ish. 6.25. The other way you could do it is to use the Paul equation. So oh shoot, -6. So either way works. So cool. Well, there you go. Hope that helps. Thanks for watching.